And let's talk about equilibrium. So I'm going to close that. This is going to be really our first look at a simple mechanism. Okay? So let's suppose we have a very simple first order equilibrium going. And a good example of this might be something like isomerization. You know, perhaps a cis isomer becoming a trans isomer through time. Okay. So now, and we'll just impose that both of these are first order to make life easier. Okay. I don't have any example of this in the Mathematica model, but I did want to just remind you, first order reactions, right? Exponential, as we saw. So what we do is we break up these reactions into two forward reactions. So I'm going to say A goes to B with rate constant K forward, and B goes to A with rate constant K reverse. Okay, and so now this is really important because this is going to be how we start to create a complex mechanism. So when I start to write now the rate of A, I'll write it over here. I'll say dA by dt. And I'm going to absorb the negative sign. We know that we put the negative sign there for A. But I want you to start getting into the habit of recognizing that for the reactant, it's going to be negative K forward times A. Okay, that takes care of our first reaction. So then what about this second reaction? Okay. Well, I'll just put this over here in the just on the side. We know that we could write that in terms of B. And we could write that as dB by dt equals K reverse now times B, because it's all about the reactants. Okay? But what we really want to do, and this is what makes it complicated, we want to think of this as a total rate law, a total differential expression. So now I'm going to take advantage of the fact that negative dA by dt equals positive dB by dt, right, from the relative rates. And so now what I can say here, my total dA by dt, it's going to be negative K forward times A plus K reverse times B. So this is my total rate law for this equilibrium expression in terms of A. Okay? And the reason why we're thinking about that in terms of A, because typically we would have B initial equal to 0 and A at any time plus B at any time must equal the initial concentration of A. So all that is saying is stoichiometry, right? If I have, let's say, 1 mole, just like this, right? If I have 1 molar of A, at any time in the reaction, the total concentrations have to add up to 1 molar. We're not making new mass, all right? So, but this is critically important, and we're going to get a lot of experience doing more complicated steps, okay? And I'll show you how we do it when we get to more complicated reactions. So, but for now, what I'm going to say over here, solving this thing becomes complicated, and I'm not going to make you solve it by hand, and I'm not going to solve it by hand. But now we recognize that B will have a differential rate than A because it has a different rate constant. So in other words, K forward and K reverse have different concentration dependencies. So now what we want to do is rewrite this expression in terms of things that are a little bit easier to write, okay? So I can now write, this is plus K reverse, and B at any time, so I'll rearrange this, is just going to be A0 minus A. I'm dropping the subscript T in this because I haven't technically integrated the expression yet, right? And so now, let's see here. If I do a little bit more math, just some algebra, all right, then I will say dA by dt equals negative k forward plus k reverse all times A plus k reverse times A0. And this is put into this form because, as it turns out now, this is a standard first order differential equation. And so we call that a diff-EQ. That's what some folks call differential equations. And it has a standard result. So I'm not going to show you how we solve this. As I've kind of alluded to, solving these differential equations is complicated. So I'm going to give you the solution to this, okay? And the solution becomes A at any time equals, and so this becomes kind of a complicated expression, okay? But it's not so complicated that it's impossible to understand. So k reverse plus k forward times e to the negative k reverse. Oops. Maybe it's just too complicated for me to write it in a clean way. I'm going to write it down right here where I've got more room. Okay, so A at time t. So we'll say solve. Okay. Equals k reverse plus k forward times e to the negative k reverse plus k forward t. Okay? All divided by k reverse plus k forward, all times the A initial concentration. And what I want to point out about this, it looks complicated, but it's just a first order decay. That's all that it is, right? So we recognize our simple first order decay. Let's see if I have one written here somewhere. Yes, we recognize our simple first order k is just e to the negative kt, right? And if I look at this expression, I could rearrange it and say at equals a0 times e to the negative kt. So keep that in your heads, right? Well, now if you look at this, look, at equals a0, so I could divide it out to do that, relative concentration rates. But now look, just k reverse plus k forward divided by k reverse plus k forward, that's just going to end up being a constant, a unitless constant, because the rate constant units will be the same. And they add up, and then you divide them by each other, times e to the negative kt. Even though it's k reverse plus k forward, it still gives us this first order expression, which is cool. Okay? And let's see, moving on here. So first order reactions approaching equilibrium. I'm also not going to do this full derivation. But basically what we can show is if we kind of if we were to spend more time with this and work our way through the math, what we would find is the equilibrium concentration of A can be written as k reverse divided by k reverse plus k forward all times the initial A concentration. Which also makes good sense, okay? Because now we can start playing with this and start talking about things like, well, what happens when k reverse is much, much greater than k forward? Or what happens when k forward is much, much greater than k reverse? And we can arrive at some pretty cool things related to what we already know about equilibrium, okay? And if we were to continue solving this, and now I'll note that this is approximate, because again, it's solving more differential equations which don't have perfect solutions. But what we would get as this approximate result is the equilibrium constant K, as we know, will be the B over A, right? If we're talking about our very simple equilibrium. And as it turns out, this just approximately, and to a very good approximation, just ends up equaling K forward over K reverse, which makes sense when you really think about it, right? When you think about a simple equilibrium, it will be related to the forward reaction over the reverse reaction, because the forward reaction creates B, the reverse reaction creates A, so these are in kinetic competition with each other, right? And once we know with equilibrium, once those concentrations have stopped changing, right? Like now that's stopped changing, and now this has stopped changing. These concentrations are going to give us our equilibrium constant, okay? Now, there's a whole bunch more that I wanted to say on what's called relaxation methods, which is what this graph is all about. But I'm only going to talk about this very, very briefly. So this is an experimental way of looking at Le Chatelier's principle. Okay? So this is pretty cool, and this is actually stuff I do in my own research. But what we would see in these relaxation methods, let me draw this graph here a little bit bigger, okay? So suppose we're doing some reaction, right? And we're monitoring its progress. You know, maybe we've monitored the reactant, and it looks something like this. And we've monitored the product, and it looks something like this. And let's suppose we enact a change. We attempt to shift the equilibrium. Perhaps we change the temperature of the reaction, or we add more reactant, or we change the volume, right? A number of things that we could do to perturb this equilibrium, okay? Then what we would observe, depending on how we've perturbed the equilibrium, is another exponential either growth or decay, depending on which way we've shifted the equilibrium, okay? So for example, this is showing you different temperatures, right? And we're going to get into that next. But suppose by increasing the temperature, let's just suppose here, that by increasing the temperature, it favors more reactants, okay? So that means, in other words, maybe we have an endothermic reaction, right? So suppose endothermic. So if I increase the temperature, okay, I'm going to increase the production of B, right? So then now what I would see here is more B getting produced, but it would be another one of these exponential rises, and now we have a new equilibrium amount. And so we would see, let me label this, we'll say that's A and that's B. And so now if we've increased this temperature, right, to shift the equilibrium to producing more B, then more A would be consumed, and correspondingly we would see something like this, okay, right? And now, as you might guess, this would actually increase the value of the rate constant, which is what we would expect for an endothermic reaction as we increase the temperature. All right? Okay, very good. So what I'm going to do